Hey everyone, welcome to the second video on our numerical methods stuff. So this video is going to talk about two potential improvements to Euler's method, the basic finite difference scheme we talked about in the last video. So in this case, we're basically still looking at just tangent line approximations because that's all we really have since we're doing first order equations. But we can do things a little bit better than just the standard one that we talked about last time. So let's go ahead and jump on into that. So in the last video, we talked about the basic Euler's method, which resulted in an equation that looked like yn plus 1 equals yn plus f of tn yn times tn plus 1 minus tn. And what this really comes from is saying that my derivative looks like a finite difference. So f of t and yn, and I'm saying this is approximately equal to a finite difference approximation to the derivative, which in this case is a forward difference approximation. Yn plus 1 minus yn over tn plus 1 minus tn. And if you solve that out, you get what you should get for the next point on the curve. Now, what we want to talk about in this video is that maybe this isn't the best way to set up these finite differences. So we're going to talk about two other ways you can set this up and talk vaguely about what they do and what they help with. And then the next video, I'll actually go into more of the details as to how you actually show these are better than the original method. So the first one is using a backwards difference. And what this comes down to is saying that f of tn yn, instead of being yn plus 1 minus yn over tn plus 1 minus tn, it's the point before that. So this is yn minus 1 over tn minus 1. And if you rearrange this to solve for yn in terms of yn minus 1, you get something like this. Yn equals yn minus 1 plus f of tn yn tn minus 1. Now, the main issue that you'll see here is it's not explicit, right? So up in the basic Euler's method, once you know yn, you can solve for yn plus 1, because y plus 1 is the only spot that occurs on the left-hand side. In this case, there's something different. There's a yn here. There's also a yn here. So this is an implicit definition, or an implicit method, because it doesn't solve for yn explicitly in terms of yn minus 1. Yn is on both sides of the equation, and it's inside the function f. So the ease of solving this depends a lot on the function f. Although you can usually get computers to solve it for you, it involves some sort of like system of equations solution thing, where the computer is more than willing to do pretty quickly. Doing it by hand, though, whether you can do it or not, depends a lot on the function f itself, whether or not you can actually solve this. Now, the main reason this is better is because it ends up being more stable than other methods, than the forward difference method. Now, we're not going to talk too much about stability in this class really at all, but the idea is that you can get away with a lot more with this method than you could with the original one. For example, in the original method, if your step size is too big, the method's unstable and it's just not going to converge for pretty much any solution. Whereas in this case, you're still going to get convergence for any choice of time step. It just might not be great, but it's not going to blow up off to infinity because the method's unstable. That's the main difference. You would choose the backwards difference over the forward difference. And normally, if people are doing Euler's methods, they're using a backwards difference scheme just to make sure they get this extra stability. Now, the other way we can think about this is doing some sort of average of the two, right? Maybe I want to, instead of thinking of it at just the value at the beginning or the end, maybe I want to take the average of those two values and use that as my slope. So this is some sort of a centered difference approximation. And the idea here is that I want to approximate dy dt not just by the value at the beginning point or the value at the end point, but I want to approximate it by the average of the two. So f of tn yn plus f of tn plus 1 yn plus 1 over 2. And I'm going to want this to be yn plus 1 minus yn over tn plus 1 minus tn, as we had before for all our other methods. This one looks a lot more complicated, but what you'll see if you actually do all the calculations out is this actually gives you an extra order of accuracy. Now, what do I mean by order? That will be the content of the next video. But this is an extra order of accuracy the same way that doing a centered approximation gives you an extra order of accuracy when doing any sort of difference approximation like this. It's closer to the derivative because you're doing sort of an average of the two sides instead of doing one side or the other. If you average them out, you get a better result, and it's closer to the actual solution than either one of the original ones. So extra order of accuracy, but it's still an implicit method. So it's more complicated to solve, but it gives you an extra order of accuracy, which actually well outweighs how hard it is to solve. In general, this sort of approach is also known as Hume's method, and you'll see it written out that way in section 8.2 of the book, where they talk about Hume's method. This is what they're doing. They're doing something like this to get their approximations. Really, the only thing is they're using a centered difference instead of a backwards or forwards difference like the Euler or the backwards Euler would do. All right, those are the main points for this video. The next video is probably going to be a lot longer, and in that one we're going to be talking about what we mean by order of accuracy, how we talk about order of accuracy, and sort of how it all comes together to why these methods, should work. And it's going to be a lot of Taylor series type stuff. All right, thanks for watching, and I'll see you in the next one.